Good morning. The topic of today's class is thermal expansion. What is the topic of today's class is thermal expansion. To understand this topic, I am taking three different type of objects here. One is the 1D object, that is rod. Another is 2D object, that is the plate. And third one is the 3D object. This is cube. Cube. Clear? This is rod 1D object, one dimensional object, or it is also called the linear object. Or the example of linear object is rod. It may be a wire also, and this is 2D object, two dimensional object, that is plate, having two dimensions, length and breadth. And this is a cube having three dimensions, that's why it is called 3D objects. When the rod is heated or heat is provided to this rod, what will happen? The length of this rod will increase. It means the dimensions of rod will change. When the heat is provided to this plate, the area of this plate will increase. It means both dimensions, length and breadth of this rod will increase. And when the heat is provided to this cube, then its three dimensions, length, breadth and height, all the three dimensions will increase. So this type of the expansions of the object, because of providing the heat to them, is called thermal expansion. What is thermal expansion? Simply we define the thermal expansions when the matter is heated. When the matter is heated without change in its state, without change in its state, the matter expands, or this expansions in the matter is called thermal expansions. Here you are seeing the three different types of the object are taken by me. Length, when rod is heated, its length is increasing. It means one dimension change in its the rod. The change in it, one dimension of the rod is changing. That is, such type of the expansion is called linear thermal expansion. Thermal expansion. Clear? When the plate is heated, its both dimensions are changing. It means length and breadth of the plate both are changing. That such type of the expansion is called superficial, physical or aerial thermal expansion. Thermal expansion. Or when the cube is heated, all the three dimensions of cube are increasing, then such type of the thermal expansion is called volume or cubic. Volume or cubic thermal expansion. Thermal expansion. we conclude there are three types of the thermal expansions. One is linear thermal expansion, second one is the superficial thermal expansion, and third one is volume of cubic thermal expansions. Linear thermal expansions, in case of linear thermal expansion, only one dimensions of the object will change, and in superficial thermal expansions, this type of the expansions occurs in 2D objects. It means two dimensions of the object will change. Volume thermal expansions, in such type of the expansions, all the three dimensions of the object will change. Clear? What is the cause of the thermal expansions? Cause of thermal expansion. Thermal expansion. On the basis of atomic theory of matter, what is the base? Atomic theory of matter. Of matter. The potential energy curve of a actual crystal is asymmetric. Potential energy curve of a true crystal is asymmetric. Which type is asymmetric? It is not symmetric. Asymmetric. So which type of the potential energy curve of this crystal? Here I am on x-axis. I will take the interatomic distance, and on y-axis I will take the potential energy. On x-axis, this is the interatomic distance, and if we draw the curve potential energy versus interatomic distance for a crystal, it is this type. Curve is this. Such type of the curve is this. This curve is asymmetric in nature. It is not symmetric in nature. Here interatomic distance is taken r. On x-axis interatomic distance, r means interatomic distance. Interatomic distance or interatomic separation. Here is potential energy. On y-axis I am taking potential energy. EP, potential energy. When the atoms of a molecules of a crystals are at a distance r0. This is r0. Or this is the case of the temperature T is equal to T0. The atoms of these molecules, or simply we can say molecules, is having only negative of the potential energy. From this point, this is origin, upward from the this x-axis or origin are taken positive and downward negative. This potential, it is having only potential energy. The vibrational energy possessed by the atoms on these points is very small, because the this range R0 is approximately equal to 1 angstrom, or 10 into 10 to the power minus 10 meter. That is equal to 1 angstrom. And the amplitude of oscillations, order of the amplitude of oscillations of the atoms when they are at a distance R0 is amplitude of the order of amplitude of the vibrations of the atoms is 10 raised to the power minus 11 meter, which is very small. That's why it is not considered. When the temperatures of the atom is increased or molecule crystal is increased, the interatomic separations becomes R1. Interatomic separations becomes R1 here. This is atoms of the molecule starts to oscillate between 2 points A and B, or this occurs at T is equal to T1. Here T1 is greater than T0, and in this case the molecules of not the molecules, the atoms of the molecules of a crystal starts oscillates between point A and B. Therefore, they are also having some vibrational energy, E1, and that is also negative, but it is greater than 2 EP, and the amplitude of oscillations more also increases. Further, the temperature increases, the interatomic distance becomes R2, and the molecules of the atom starts oscillates with higher amplitude A dash and B dash, point A dash and B dash. In this case, they are oscillating between about R1, and in this case they are oscillating about R2. So as in first case there is no expansions in the matter when of a crystal, and when the atoms are at a distance R0. When atoms reaches that distance R1, the amplitude of order of amplitude of oscillations increases. It means the separations between them will increase. This indicates matter expands. On increasing the temperature further, T is equal to T2. The separations of the separations between the atoms further increases. It means the matter further expands. So thermal expansions can be explained on the basis of potential energy curve versus interatomic distance. And potential energy curve of a true crystals is asymmetric, because of that matter expands. Now we will discuss about the types of the thermal expansions in detail. Now is linear thermal expansion. Linear thermal expansion. Thermal expansion. As I told you, this type of the expansion occurs in 1D objects like rod and wire. When a rod and wire is heated, there is a change in its length. That change in its length is directly proportional to the original length of the wire or rod, and it is also directly proportional to the change in its temperature, delta T or delta theta. Clear? From these equations, we will obtain alpha L naught delta T, where alpha is called coefficient of linear thermal expansions. Coefficient of linear thermal expansion. Here I am saying that alpha is coefficient of linear thermal expansions, and it is not a constant of proportionality. Why it is alpha is not a constant of proportionality? Because alpha is not constant for a given matter or a given solids, because it changes because it changes on the temperature ranges, because it changes on the temperature range as well as the distance. Alpha is not a constant, is not a constant, because it changes or varies with respect to distance as well as temperature range, because it varies with respect to temperature range and distance. Clear? When it change with temperature, when the alpha coefficient of linear thermal expansion changes with temperature, range, it means alpha is the function of temperature. Alpha is the function of temperature. Total expansions in the rod, delta L. Total expansion in the rod or wire is given as integrations of alpha ft, integrations of ft dt, temperature, this is not time, into delta L, temperature range is this, delta L. Clear? When it changes with respect to distance, when alpha changes with respect to distance, when alpha changes with respect to distance, as follows: alpha is equal to ax plus b, ax plus b, where a and b are constants. The total change in length, total change in length in length is given as integrations of ax plus b into dx into delta t, delta L. That's why it is not a constant. Linear coefficient of linear thermal expansion is not a constant, and it varies with respect to distance as well as the temperature range. Further, the unit and dimensional formula, dimensional formula of alpha, unit of alpha in SI system in SI system is per Kelvin is written as K minus 1 or per Kelvin. Clear? Or you can write it in such a way Kelvin. In CGS system, its unit is per degree Celsius or per degree Celsius. Degree Celsius. Or you can write it in such a way per degree Celsius. Dimensional formula of alpha of coefficient of linear thermal expansion is K minus 1 or theta minus 1. Theta is representing temperature here. You can write it in such a way also M0, L0, T0 and K minus 1. Or you can write it in such a way also M0, L0, T0, theta minus 1. Here the T, capital T is temperature in this dimensional formula, or here in delta T, capital delta T is or dt is the change in temperature. Delta L versus delta T graph, delta L versus delta T graph for a rod or wire of given length L naught. Here from the formula of thermal expansions, delta L is equal to alpha L naught delta theta. If this is a straight line equations, equation of a straight line, straight line equation having the slope with delta t axis. We can draw this graph in such a way. On y-axis, I will take delta L, whereas on x-axis, I will take delta T, delta L and delta T. Such type of the graph will be obtained. And the equations of this graph is, this line is this, and that is the slope theta. Tangent of this slope, here from this points I draw a perpendicular on time axis 0 and 0. This origin A and B from the triangle, right angle triangle OBA. Tan theta becomes delta L by delta T, and from equation 1, this is the equation 1, this becomes delta L by delta T is equal to alpha L naught. This is true only when the length of the solenoid remains fixed and temperature range is n- not non-uniform. What is it? Is the uniform. It is uniform. Second case, graph delta L versus L naught. This is also an straight line graph, and in this graph, what will happen on by axis I will take delta x, delta L, and on x axis I will take delta L naught. L naught. Here is delta L, or this is L naught. This is the origin point O. The graph is this type. Similarly, this point is A. Draw a perpendicular from point A on length axis. Then the slope tangent of this slope is tan theta becomes equal to delta L by L naught. That is equal to alpha delta theta. Here the temperature range is constant, length is varied. Such stuff. This is the linear thermal expansion, and now we will discuss about the superficial thermal expansion. Superficial thermal expansion. Superficial or aerial thermal expansion. Aerial thermal expansion. Clear? Coefficient of superficial thermal expansion is beta, and the change in area is given as beta original area into change in temperatures, where beta is given as delta A change in area over A delta T. This is called the coefficient of superficial thermal expansion. Coefficient of superficial thermal expansion. Thermal expansion. And the unit and dimensions of beta is same as the alpha. It means in SI system unit of beta is per Kelvin. In CGS system unit of beta is per degree Celsius, and dimensional formula of beta is also same, that is m0, l0, t0 and theta minus 1, or theta you can replace it in such a way m0, l0, t0, k minus 1. It is not also a constant, it varies with the temperature range as well as the area. Similarly, third is volume thermal expansions. Volume thermal expansion. Coefficient of volume thermal expansion is gamma. Gamma change in volume is equal to gamma original volume into change in temperature. Same, it is also determined with same as we determine the linear thermal expansion. Gamma is equal to delta V by V delta T. This is called coefficient of volume or cubic thermal expansion. Thermal expansion. And its unit is same as the unit of alpha and beta per Kelvin in SI system and per degree Celsius in CGS system. And dimensional formula is also same as the dimensional formula of alpha and beta. Clear? And it similarly alpha and beta, it is also not a constant. It varies with respect to temperature and volume. The relations alpha, beta and gamma. Relation between alpha, beta and gamma. It is alpha ratio beta ratio gamma is equal to 1 ratio 2 ratio 3. This is the relations. And first, second is beta is equal to 2 alpha and gamma equal to 3 alpha. Now the third relations will be a fourth relation is the relation between beta and gamma. With the help of these two relations, I establish a relation between beta and gamma. Gamma is equal to 3 alpha divided by beta is equal to 2 alpha. This relation is divided. This relation is divided by this relation. Alpha will be cancelled out. Alpha gamma is equal to 3 by 2 beta. This is the fourth relations. Here now we will check the proof of these relations. As we know, proof of beta is equal to 2 alpha. As we know, the area is given as L into B. Now differentiate these equations with respect to temperature. Differentiating with respect to temperature, dA over dt capital T, this becomes dL over d capital T into B plus L into dB over d capital T. dL over d capital T, this becomes is equal to alpha L into L, or this becomes alpha B into B, dA over dt d capital T, d capital T, alpha L thermal expansion, linear thermal expansion in length into L into B, plus L coefficient of linear thermal expansion in breadth into B, taking out common L into B, alpha L plus alpha beta. LB is area from equation 1. dA over d capital T becomes A into alpha L plus alpha beta. You can write it in such a way, dA over A into dt is equal to alpha L plus alpha beta. This is called coefficient of superficial expansion or areal expansion, then becomes alpha L plus alpha beta. for anisotropic substances. This is for anisotropic substances, anisotropic substances or a seat. For isotropic substance, alpha L becomes equal to alpha beta. That is, beta is equal to 2 alpha. Similarly, we establish the third relation, that is the gamma is equal to 3 alpha. Gamma becomes alpha L plus alpha beta plus alpha B plus alpha T. Coefficient of linear thermal expansion in L, coefficient of linear thermal expansion in breadth, coefficient of linear thermal expansion in thickness. This is for an isotropic. Anisotropic substance. Clear? Some other important informations about the thermal expansion. Thermal expansion is minimum in case of solids. Thermal expansion is minimum in case of solid. Thermal expansion, either linear thermal expansion, superficial thermal expansion, or volume thermal expansion, is minimum in solids and it is maximum in gases, because the interatomic force in solids are strongest, whereas in gases they are weakest. Third is solids are having all types of the thermal expansions, all types of thermal expansion, mean thermal expansions. Linear thermal expansions, superficial thermal expansion, and volume thermal expansions, according to their dimensions. Whereas liquids and gases are usually having only volume or cubic thermal expansion. Thermal expansion.